Hi everybody, welcome back, and we're going to talk about merge sort, heap sort, and give a overall analysis and review. So this is part 3 of the sorting lectures. There's a lot of stuff here, and I've, even with the 3 lectures that I'm giving you, I've only brushed over the topic. So do some web research, look through your textbook, talk to me, participate in discussions. All these normal things are also important in order to come to a full understanding of sorting algorithms, their importance, analysis, and all this. This is very important and big topic, and you'll use this a lot. A lot of times you're going to just end up using an algorithm that's already written for you or access it in a C library or something like that. But it's very important to understand what's going on, and especially to get the runtime analysis so you know when to use which sort. So without further ado, let's talk about merge sort really quick. Merge sort is a lot easier to explain than any of the other sorts. It doesn't necessarily make it extremely easy to code, but explanation conceptually is very easy to understand. So we have the same sorted array that we ran on quicksort: 9, 20, 6, 10, 14, 8, 60, and 11. And we're going to merge sort it now. So what merge sort does is recurses. Really big recursion, recurse, and then merge. And that's it. It's 2 steps. The recursion part is really easy. You just break it in half and recurse half of each part. And that's exactly what we're going to do here. So you find the midpoint in whatever data structure you're using, and you send half of it down a recursive call and the other half down a recursive call. So let's analyze that, and I'll explain the merge and the rest. So broken it down into 2 pieces now: 9, 26, 10, and 14, 8, 60, 11. Now, since it's a recursive call, we're just going to recurse again. So the first step in the next recursive call is to recurse. 9, 20 is then the little 2-piece array that we end up in 6, 10. And then the other one is split into 14, 8, and 60, 11. And let's stay over here. So now we're going to recurse again on the third call, and we break it into 2 pieces, 9 and 20. Now at this point, you're hit the base case because there's nowhere more to recurse. So this is sorted, right? This is just an array of sorted 9, an array of sorted 20, sorted 6, 10, etc., etc. So all these individual pieces are sorted. Now, and pop back up, and in order to proceed through the algorithm, you have to do a merge. So first recurse, and then merge. So we're at this level here where we have 9 and 20. Recurse down to 9 and 20. Those are trivial cases. Pass back up to the case where we just recursed, and now the second step here is to merge these 2 elements. So merge this side 9 with this side 20. And so what we do is we just basically have 2 arrays. I guess I'm going to go with arrays. It can be any type of list structure or any kind of other data structure. So we have 2 arrays, and we're going to simply start at the beginning of each one because they're sorted now, and we're going to move forward and compare the 2 elements and pick whichever one is least. So it's a simple ON algorithm, and all we're going to do is stomp forward and pick the smallest one. So in this case, we have only single elements, so we're just going to compare the first element, 9 to 20, and 9 is left. So we stick that in the first slot. 20 is the only thing left after this one's exhausted. So we put 20 in the second slot. Boom, we're done. 9, 20 is sorted. Same thing here, 6, 10, 6, 10 sorted. 14, 8, 8, 14 now, because now we have to flip them, right? So we're going to, actually, I'm sorry, we don't flip here because that's more insertion sort. What we're doing is we're putting in the third-party array. So this does use space, and that's the trade-off here that we'll get to, is when you have this point, when you're at this point, and you have single elements, 14, 8, you make a new array, a new data structure, and you stick the lesser of these 2 in the first element item, and then you keep doing so until you have them all into the new data structure. So we copy the 8 and copy the 14, not flip, but copy. And now we have a sorted copy. And then again, 16, 11 can be translated into 11 first, copied into the first position, 16 into the second. Now, perhaps more interesting to go up one more level. So now when we pop back up another level, we have the 2 element pieces sorted, and now we need to merge those. So now remember, both sides are sorted already, so we don't have to worry about individually sorting each thing. We can just merge them together, which turns out to be a lot easier problem. Because again, we start at the first element of each, 9 and 6, compare, see which one's smaller. The 6 is, so we put it in the first item, copy it to the first item. And now we move over to 10 and take 9 and 10, and 9 is left, so we copy it into second position. Now we move over to 20 here because we're done with that. We have 20 and 10, 10 is left, so we move over here, copy to 10, and now we're done here, so we just copy to 20. And so it's a simple O of n algorithm. You can just move through the array spots and compare. Same thing over here, 8 and 11, compare, 8 goes first. I move over here, 14, 11, 11, and then 14 and 60, 14, 60, 60. And I think you see how this works now. So then these two merge. These two are all sorted already. You merge those together, and you create the answer. Now, what's ingeniously brilliant about this, with insertion sort, you have to figure out a good pivot, and you have to worry about the bad case where you've chosen to pivot badly through perhaps no fault of your own, and you ended up with an O of n squared algorithm. Merge sort, you don't have that problem. You're always splitting it in half, and so you are guaranteed to have half as many steps each time. And so the number of steps here is always log of n. And again, we're not going to prove this and explain it all that well, but please do ask if you have any questions about it. And I'll do my best. This is a mathematical concept where if you split something into halves each time, you end up with log of n of those steps. And each time you're merging, that's an O of n operation. You simply merge each array together. You're only marching through the array once, basically. And so it's an O of n operation. So this is times O of n. And you end up with an n log n sorting operation. Now, in case it's not obvious at this point, n times log n, O of n times log n rather, is really the best case that you can do on average for sorting. So this is a spectacular result because it's also the worst case. So a merge sort, O n log n is the best case, the worst case, and the average case. It's all of those things together. And so you're guaranteed to get this performance, but you're also not guaranteed to do any better. And you do have to think about that because remember with bubble sort, it's possible to get an O of n. Also with insertion sort, it's possible to get O of n. And I think those are the two. So it's possible to do better using one of the other sorting algorithms, but if you want to be guaranteed to do worse than n log n, if you're using very big sorting data structures that might be important, then merge sort is a good place to start. The other drawback of merge sort is that it requires space. Like I said, instead of swapping positions, you're actually copying into new data structures. So you require O of n of memory in order to do this merge sort. And that can be really bad in some situations. If you have a very, very, very large data structure, you can't afford memory-wise to copy it. You might not have enough memory to do a full copy, especially if you're talking about a gigabyte data structure. That's huge. So making a whole big copy of it is just not acceptable. So again, another drawback you might want to consider another sort. So really quick, I'm going to explain heap sort. Heap sort in 2 seconds. Heap sort is put things in a heap, take them out again, priority queue rather, put them in a priority queue, which is we call a heap, and we'll talk about that, and then remove them one at a time according to their highest priority, which is the definition of how we remove from a priority queue. That's it. Now the problem is I haven't taught you anything about priority queues and heaps yet, so hold that thought, and we are going to learn that in a couple of weeks. But for now, just know the heap sort is basically using a heap, which we'll get to, and you'll see at that point how easy it is to pull those in and out. Heap sort is also guaranteed for n log n. The big difference with heap sort is you have to create a heap, and as you'll see, heaps are complicated. And when they're complicated, that means they're complicated to program as well. So merge sort, much easier to program. Quick sort, really easy to program. These are much more powerful algorithms for getting something out quick and dirty without having problems. But heap sort is powerful in that it may not require that memory, extra memory, but still be able to guarantee n log n, because that is also an n log n algorithm. So I think I went through the quick analysis of all the algorithms. So for quick review, bubble sort, it's possible to get O of n, but in the worst case and in the average case, really, you get n squared performance. Merge sort, you get n log n guaranteed, but you have to spend some extra space, O of n, in order to get that. Heap sort, you don't have to spend the space, you get O of n log n, but it's horrible to program. Quicksort, conceptually more confusing, easy to program, and you get n log n most of the time, but you do have to be aware that that pivot point can screw you up, and you might end up with n squared performance. So there is no magic bullet sorting algorithm, you'll notice. They all have positives and negatives, and there isn't one that you should go, I'll just always use that. That being said, you should always try to use an n log n one, but it might depend on the particular kind of data that you have. So we'll talk about this more in discussion, and you'll see, and you're going to implement Mergesort for a lab, which I think is very interesting. And I hope you had some fun.